Now, I've said as much as I want to say right now about arc length. If you take what we did, especially with my corrections, and apply it, you're going to be able to do the easier problems. Hopefully, then you'll understand some of the little glitches that can occur and some of the ways you can apply it to more challenging problems. I really think that most of you will be able to do that without much trouble. Wouldn't surprise me. That also wouldn't surprise me if you had some questions. So, you know, naturally we'll take questions and try to clarify anything that needs to be clarified. But we're going to switch gears to actually another section of the chapter that hasn't yet been assigned, but I want to anticipate it. And we've done much of this already, so this shouldn't be too difficult. I will say that the expressions that you can get out of this are the ugliest expressions you're likely to have ever seen in your mathematical career, and maybe about as ugly as anything you're going to see. But it's just that they're long and tedious, not that they're particularly difficult. Difficult to get them right because there's so many steps, but not that difficult to do. Okay, well, we won't worry about that just yet. I'll allude to that when it gets to the time. If we have a position function, a curve, okay, we know that we can get our velocity function just by taking the derivative of our position function, and that that's going to give us a vector that's tangent to our curve. And we know then that there would be a second derivative, which would be our acceleration function, and that acceleration will have components parallel to the v of t and perpendicular to v of t, the parallel and perpendicular components that we've already talked about. Okay, we want to develop a little more detailed picture of motion along the curve. So we're going to define the unit tangent vector. Okay, now if this is your velocity vector, well, we don't know if the velocity vector is more or less than, has magnitude greater or less than 1, but we'll assume magnitude's about 4. And that our unit tangent vector is going to look like this. What's the unit tangent vector? It's a unit vector that's tangent to the curve. And since the velocity vector is tangent to the curve, that means our unit tangent vector has got to just be the velocity vector divided by its magnitude. Then we have our normal vector, and we've already looked at the normal vector, but I think we've talked about the normal vector. Just as what you get, if you project the acceleration vector and the velocity vector to get its component in that direction, and then subtract that component from the acceleration vector, you get a normal vector, and it's an inward normal vector toward the inside of the curve. And a unit normal vector then would just be the unit vector in the direction of that normal vector. Okay, now I'm going to let big N stand for my unit vector, and I'm going to claim that, first of all, the derivative of our unit tangent vector has to be perpendicular to our unit tangent vector. And it's also got to be directed in the direction in which the unit tangent vector is changing. Okay, and that would be toward the inside of the curve. Well, it's really very easy to establish this. If we have our unit tangent vector at time t, and our unit tangent vector at some later time t. Now this picture doesn't represent the way it would look on this diagram. This is just a generic picture of t of t and t of t plus delta t. Well, the derivative of our unit tangent vector is approximately equal to the change in t divided by delta t. And then as you let delta t approach 0, that ratio approaches your derivative, the delta t over the change in your unit tangent vector divided by delta t approaches the derivative of your unit tangent vector. Okay? So what do we know about this triangle that's formed here? Well, delta t is this vector, this blue vector here, from t of t to t of t plus delta t. Again, think, if I add delta t to t of t, I get the big T of t plus delta t. Okay? Which means that our delta t is this minus this. If this plus this equals this, then this equals this minus this. An idea that hopefully you've been used to for most of your life. What can you tell me about this triangle? Well, somebody said, well, it's a right triangle. Well, no, but it's kind of close, the way I've drawn it. It can't be a right triangle because T, big T unit, your unit tangent vector is a unit vector. It means this side is equal to this side, meaning that this is an isosceles triangle, meaning that this angle and this angle are equal. Well, they're equal, but this angle here, this third angle of the triangle isn't zero, is it? Okay, so these two are equal and this isn't zero. What are these two equal to? Well, the angles add up to 180 degrees, so these two have to add up to 180 degrees minus whatever this angle alpha is. Okay? And if alpha is small, that means they're going to add up to something pretty close to 180 degrees, but it's not going to be 180 degrees. Now, two things that are equal that add up to 180 degrees would both be 90 degrees. Since they add up to a little less than 180 degrees, these angles are both a little less than 90 degrees. However, as our delta t approaches zero, this angle approaches zero because, of course, these two vectors approach one another as a limit. So our angles approach 90 degrees, and in the limit the angle will be 90 degrees, which means our delta t approaches an angle that's perpendicular to t. So that our derivative of our unit tangent vector has to be perpendicular to the unit tangent vector. And I've written some stuff out about this. Say as delta t goes to zero, this angle alpha goes to zero, so theta 1 equals theta 2 approaches 90 degrees. So the limit as delta t, little t approaches zero of big T of t plus delta t minus big T of t over delta t, which is the limit that defines your derivative, is dt over d little big d, the derivative of your unit tangent vector d big T, say, over dt, the time increment, and that has to be perpendicular to your unit tangent vector. Okay, and just a little more about isosceles triangles, and also the centripetal acceleration thing, that your perpendicular component is v squared over r, where r is a specific circle called the osculating circle. We're not going to talk about that quite yet today, although people said they've already seen that in their dynamics class. So we'll clarify the osculating circle and put it in this context. So it's more than just a formula to you. Okay, so that's our picture. Our derivative of our unit tangent vector with respect to time then is perpendicular to our unit tangent vector. Therefore, it's normal to our direction of motion. And if we divide by its magnitude, divide that derivative by its magnitude, we get this vector, this capital N vector that I call the unit normal. Okay? And some people use a small n, some people use a big N, but I'm defining that to be the unit normal. What's the advantage of having a unit tangent vector and a unit normal vector? Well, for one thing, it makes projections really easy, and for another, those two vectors define a coordinate system along with their cross product that kind of follows you along and has significant meaning for your motion.